So hello everybody. So as the title indicates, this work is just a first attempt to try to solve numerically controllability problems for PDEs by using deep learning based methods. This work is still going on. It is in collaboration with Carlos García Cervera from University of California, Santa Barbara, and Mathieu Kessler from Universidad Politécnica de Cartagena. And actually we are in the very beginning, right? So this work is also supported by Fundación Seneca, which is the Agency for Science and Technology of Murcia, under the mobility program Jiménez de la Espada. Okay, so the main goals of this work is to try to explore the use of deep learning-based algorithms to approximate numerically controllability problems for PDEs. And also, it is important to try to get error estimates for the so-called generalization errors that I will introduce later on. So the outline of the presentation is the following. I will consider a very, very simple toy model, actually the boundary controllability problem for the linear wave equation. This is just for simplicity, for clarity in the exposition, but the method you will see can be applied to many other controllability problems. So then we will adapt the so-called physics-informed neural networks, PINs, to approximate numerically the above toy model. We also prove some error estimates for the generalization error. Then I will comment about the numerical implementation via the deep XDE Python library. I will present some very preliminary numerical simulation results. And then I will comment, maybe this is the most interesting part, how this method can be extended to other type of PDEs, controllability problems, and mainly in those cases where high dimensionality plays a role, which is the main concern of deep learning. So this work is based on two previous works by Karniadiakis and his collaborators, where they introduced the now very famous PIMS algorithm. There is the pioneering work in Journal of Computational Physics in 2019, and this is a recent review paper about the library Deep XDE. Okay, so let me present the exact controllability problem that we are going to consider. So giving initial data in some functional space and a fixed positive time, capital T, large nodes, the exact controllability problem for the wave equation amounts to find a boundary control U, which is acting at the right-hand side at the extreme x equal to 1, and such that the solution of this wave equation satisfies the so-called exact controllability condition at capital time T, right? Okay, so this is a very toy model which has an explicit solution, actually for T equal to 2 divided by C is the velocity. There is an explicit solution for both the states Y and the control U, which can be computed easily by using D'Alembert formula. But we will use this model to check accuracy of the method that I'm going to propose right now. How to approximate this problem by using deep learning algorithm or the PIN algorithm. So the first step is to try to design an artificial neural network, Y hat, depending on the position x time t, and a set of parameters theta. And this is a surrogate of the through solution of the through state Y, depending on x and time. Second step is to choose a training data set in the space-time domain 0,1 times 0t. Third step is to consider a loss function. In this case, we will consider a weighted summation of the L2 norm of the residuals for the equation, boundary, initial, and final conditions. Fourth step is to train the network. It amounts just to minimizing the loss functions defining the previous state with respect to the set of parameters theta. So once the training process has ended, optimal parameters theta defining the neural network are computed, and eventually are used to get predictions about the state. And the control UT, which is approximated just as the trace of the surrogate states at the boundary point is equal to 1. That is, the approximate control U hat at time t is equal to y hat at position 1 and time t, right? Okay, so now let me explain more in detail this fourth step. So for the neural network, we are going to consider a multilayer perceptron, a multilayer neural network, which had two input canals, position and time, and an scalar output y hat. So precisely y hat is constructed as follows. So here we have the two input channels, X and time. So the data go through all the network. So here in the first hidden layers, what arrive is the multiplication of a matrix W by the data, and we add some bias vector, right? And then we apply an activation function, which in our case should be smooth. Actually, we would choose the hyperbolic tangent. And then the data go to the next hidden layer and the same way. And finally, for the output, we just multiply the data of the previous layer by a matrix, and then we add the bias. So the set of parameters defining the neural network is the elements of the matrices W and the vector of biases B, right? So there is a theorem by Barrow which says that the functions we want to approximate, in this case is the state and the control is smooth, then just a single layer neural network is able to approximate with accuracy that function because it is a Barrow function, right? So it means that this the selection of the neural network is a good election to approximate a problem because the function to be approximated will be smooth. Okay, so what about the training data set? So we select some data in the space-time domain. So here the horizontal line is for space, the vertical line is for time. And here we select a number of points which could be uniform, could be pseudo-random, could be random, etc. As I said, both in the interior domain and all around the boundaries. So this corresponds to x equal to 1, this corresponds to time equal to 0, this is for x equal to 0, and this is for the final time capital T. In our case, this picture corresponds to a Sobol distribution of points. What about the loss function? Well, the loss function is composed of 6 terms. The first one corresponds to the residual for the PDE. So we looked for a classical solution of the wave equation. And here there are some weights which correspond to or which are associated to some quadrature rule that one has to select. We do the same for the boundary condition. Remember is that y should be equal to 0 at x equal to 0. The same for the initial position, the initial velocity, and these two last correspond to the controllability condition. All of them are with some weights, as I said before, associated to some quadrature rule. First step is the training process. So in algorithm, what we have to do is just to minimize this function with respect to theta, right? And to do that, we are going to use the famous Adam algorithm, which is adaptive with moment, which is typically the Descent algorithm is the model of choice in most of machine learning algorithm. And we will use also automatic differentiation to compute all the derivative gradient that we have to compute in this process. And this algorithm is implemented in all machine learning softwares, for instance, TensorFlow, which is the one that we are using. Then, as I said before, the approximate control is just obtained as the restriction of the state at the point x equal to 1. So what about error estimate for the generalization error. So generalization error is defined as the distance in L2 of 0t between the exact control of the continuous problem and the surrogate control that we compute by using the PIN algorithm, right? So our goal is to get estimate for this error in terms of estimate for quadrature and the so-called training error. So let me remember the typical error estimate for quadrature errors. So if we want to compute the integral of a function on a domain D, which is in Rd, D is the dimension of X, right? So typically we apply a quadrature rule in a different ways. It depends on the quadrature that you want to choose. And the error takes this form. But here, this constant may depend on D, which is most of the cases, or it can be independent of the dimension, which is the case of Monte Carlo method. N is related to the number of points that we use for quadratura, and alpha is related to smoothness of function f. And what is training error? Well, training error is just the value of the cost function that we have minimizes during the training process. So it's just, as I said, the cost function at the optimal value of t star. And the result is this one. We have a smooth solution of a problem. So here, smoothness is important property. So then the generalization error is less than equal to constant. So this is more, this symbol is just to add here the constant. Training error in the interior domain, in the boundary x equal to 0, initial position, initial velocity, final position, final velocity, and the corresponding errors for the quadrature rule that we have used. The main ingredients for the proof are just observability inequalities for the controllability problem and the classical and well-known energy estimates for the PDE, for the wave equation. So this is very well known. I have collected here an observability inequality for this system. Actually, the proof in this paper is much more general. It is valid for even variable coefficients, right? But anyway, the important is that if we have a system like this, then the control V is bounded by a constant, the norm of the initial data and the norm of the final data at time capital T. And this is the well-known energy estimates for the non-homogeneous wave equation, right? That everybody knows. This is very, very classical. But these are the two main ingredients in the proof. So for the proof of generalization error, what we do is just to consider the difference between the exact solution and the surrogate solution, the solution that we get from PIN algorithm, and the same for the control, right? So then y hat is the solution of this PDE system. And this the solution by linearity is decomposed into two parts. Y hat 1, which is this system here, when we have dropped out the right-hand side of the PDE, and also this boundary condition at x equal to 0, and we have keep the control. So we will apply observability inequality to this system. And this is the remaining system, which incorporates the right-hand side of the PDE and this boundary condition at x equal to 0. So when we apply observability inequality, we get this term here. I mean, the initial conditions and the final conditions. Then, since everything is smooth, we can put actually the L2 norm in all the terms. And now we are going to pass from y bar 1 to y hat and y bar 2. So we get this term here. So this corresponds to training error, and we have to work a little more with these two terms. So now we apply for these two terms the energy estimates for the wave equation, and then it emerges the boundary condition, and it emerges also the residual for the PDE. So then we apply the quadrature rule, and all these terms decompose into two terms, training error plus the error of the quadrature rule. And this is basically the idea of the proof. So for numerical simulation, let me consider that very simple example. So we have implemented via DeepXDE, which is a Python library developed by the group of Kamiadakis in Brown University. So we have considered a multi-layer perceptron with 4 hidden layers and 15 neurons in each layer. The activation function is the hyperbolic tangent. The dataset for training is Sol. Optimizer is Adam, and we get some final iterations by using a quasi-Newton method. And the initialization for the descent algorithm is carried out by using a Glorov uniform distribution. And this is a summary of results for training errors for 500 interior points and 50 boundary points in each part of the boundary. So we get errors in the R2 norm for the residual of the PDE of 10 to minus 8, 10 to minus 6, the same for these boundary conditions, for the initial conditions, and for the controllability, exact controllability condition, we get something of the order of 10 to minus 8. This is the picture of the predicted solution, the solution that we get by using the PIN algorithm at each of the points, several points. If you remember, this is exactly the same solution that we get by using the D'Alembert formula. So here the approximation is actually quite well at this, in this very toy and this very simple example. Okay, what about the scope of the proposed methodology? Well, maybe one of the main advantages of this approach is that it is quite general. It can be applied to many other controllability problems for PDEs, both linear and non-linear, and with different types of control actions. The method can be also, in principle, be adapted to deal with controllability problems for parametric PDEs. So, for instance, for average control, where the dimension can be very large. And also a challenging and high-dimensional problem is to try to design a machine learning algorithm that try to approximate the operator that links initial data to control. As you have seen before, our algorithm had to be trained for particular initial data of the wave equation. So it would be nice to try to design a machine learning algorithm in which you give information about the initial data and then automatically you get the control. And this is something that we are thinking right now, but still, of course, we don't have results. Okay, and this is basically all I have prepared for you. So thank you very much for your attention.
Thank you very much, Paco. Is there any question?
Yes. Can I ask something, Carlos?
Yes, of course, yes.
So thank you, Paco. Very interesting. So independent of the control aspects, so how well does this kind of methodology approximate solutions? So in the classical sense of numerical analysis, right? Because you see, what typically happens, as you know, for the wave equation when you discretize, is the high frequency solutions are not well captured by the numerical scheme, right? So you capture well the low frequencies, but at high frequencies, I mean, you don't even see the finite, I mean, the correct velocity of propagation of waves, right? So do you think that this is so, for instance, for classical finite difference and finite element methods? So do you think that this kind of methodology can improve the performance of classical numerical methods for this?
Well, I have not so much experience, but in my opinion, I think that for low dimensional problems, machine learning algorithm cannot improve the classical methods, finite elements, finite difference. I think that the place where machine learning, the gain that machine learning has to play is in high dimensional problems. You know that solving high dimensional PDEs, dimension higher than 3, is an unsolved problem in numerical analysis. In my opinion, this is the game that machine learning has to play. But I don't believe that this technique can improve classical methods like finite difference, finite elements in classical problems in low dimension, dimension 2, 3, or 1.
You mean a space dimension, right?
Exactly.
Yeah, I see. Okay, yeah.
But this is my personal opinion. I have not so much experience.
Right.
I'm just a beginner of machine learning.
I see. Thank you, Paco.
Okay. Any other question? No? Well, we thank again Paco and all the speakers this afternoon. Thank you very much to everybody.